So we've been spending some time now thinking about the idea of a Fourier series, taking a periodic function and representing it as the sum of weighted cosines and sines. And some of you might say, well, how is this constant a weighted cosine or sine? Well, you could view a sub 0 as a sub 0 times cosine of 0t. And of course, cosine of 0t is just 1, so it'll just end up being a sub 0. But that could be a weighted cosine if you want to view it that way. And in the last video, we started leveraging some of the integrals, definite integrals of sines and cosines to establish a formula for a sub 0, which intuitively ended up being the average value of our function over one of its period, or over 0 to 2 pi, which is the interval that we are caring about. What I want to do now is find a general expression for a sub n where n is not equal to 0. So for n is greater than 0, for n is an integer greater than 0. And I'm going to use a very similar technique. To figure out a sub 0, I just took the integral of both sides. What I'm going to do now is I'm going to multiply both sides of this equation by cosine of nt. So let me do that. So on the left-hand side, I'm going to multiply by cosine of nt. And on the right-hand side, multiplying it by cosine nt, if I distribute that cosine of nt, I'm going to multiply every term by cosine nt. So it's going to be cosine of nt, cosine of nt. You might see where this is going, especially because we took all that trouble to figure out the properties of definite integrals. Cosine of nt, cosine of nt, cosine of nt, or the properties of definite integrals of products of cosines and sines, cosine of nt. And this is going to be true for all of the terms. There's an infinite number of terms here. That's what that dot, dot, dot is representing. We're just going to keep on going on and on and on. And now let's take the definite integral of both sides from 0 to 2 pi. So the definite integral from 0 to 2 pi dt, well, that's going to be the integral of this from 0 to 2 pi. And actually, let me just take that coefficient out of the integral. So 0 to 2 pi dt, so 0 to 2 pi dt, a little bit monotonous, but it's worth it. 0 to 2 pi dt, 0 to 2 pi dt, we might as well have fun while we do it. 0 to 2 pi dt, all right, 0, my hand is hurting. 0 to 2 pi dt, 0 to 2 pi dt. Once again, just integration property. I'm taking the integral from 0, the definite integral from 0 to 2 pi of both sides, and I'm just saying, hey, the integral of this infinite sum is equal to the infinite sum of the different integrals. Now, what is this going to be equal to? Well, we know from before that if I just take the definite integral from 0 to 2 pi of cosine nt, where n is some non-zero integer, this is just going to be 0. So this whole thing is going to be 0. We also know, and we've established it before, if we take, so I just used this property. We also know if we take cosine nt times sine of mt for any integers mt over the interval from 0 to 2 pi, that's going to be 0. And we also know that if we take the integral of cosine mt cosine nt, where m does not equal n, that is going to be 0. And so we know, well, here we're assuming here that n is not equal to 1, the coefficient here, so that is going to be equal to 0. This is sines and cosines with different coefficients, and frankly, even if they had the same coefficient, that's going to be 0. We established that in the last few videos. This is going to be 0, same argument. This is going to be 0. This is going to be 0. Everything's going to be 0 except for this thing right over here. But what is this thing? This is the definite, what we're taking the integral of. This is the same thing as cosine squared of nt dt, the definite integral from 0 to 2 pi of cosine squared nt dt. Well, what is that? Well, we established that for any m non-zero m, this is going to be equal to pi. So all our work is paying off. So this whole integral right over here is going to evaluate to pi. We did that in another video. And so now we can start solving for a sub n. We know that a sub n times pi is equal to this, because everything else ended up being 0, which is very nice. It's equal to the definite integral from 0 to 2 pi of f of t times cosine nt, cosine of nt dt, cosine nt dt. And so we can now solve for a sub n. We just divide both sides by pi, and we get a sub n is equal to, I think we deserve a little bit of a drum roll, a sub n is equal to 1 over pi times all of this business, times the definite integral from 0 to 2 pi f of t cosine nt dt. So if you want to find the nth coefficient for one of our cosines, a sub n, well, you take your function, multiply it times cosine of nt, and then take that definite integral from 0 to 2 pi, and then divide by pi. So pretty intuitive. And what's cool is that the math kind of works out this way, that you can actually do this. So hopefully you enjoyed that as much as I did.